They look identical on your workbench, use the exact same packaging, and both function as electronic switches. But wire them up the same way, and one will turn on when it's supposed to turn off, while the other might completely block your power rail. This is the ultimate showdown in semiconductor physics: NPN versus PNP. Failing to understand the difference between these two components is why so many custom prototyping circuits experience power leaks, unexpected logic inversions, or short circuits. Today, we are breaking down the internal physics of NPN and PNP silicon layers, mapping out how their schematic symbols tell you exactly how they function, and revealing the golden rule for choosing the right one for your next PCB design. Part 1. The silicon layout and symbol clues. To understand the core difference, we have to look inside the silicon sandwich itself. An NPN transistor places a thin p-type layer between two n-type layers, meaning its primary charge carriers are fast-moving free electrons. A PNP transistor flips this architecture completely, sandwiching an n-type base between two p-type layers. This means its primary charge carriers are electron deficiencies, commonly referred to as holes, which move significantly slower than free electrons. This physical inversion changes how we draw them on a schematic. Look closely at the emitter pin arrow. For NPN, the arrow points outward. Remember the classic maker rule, not pointing in. For PNP, the arrow points inward toward the base. Think pointing next patently. That tiny arrow is your roadmap. It always points in the exact direction that conventional current flows through the device.
Part 2. High side versus low side switching. This directional change alters how these components are integrated into a power rail. An NPN transistor is fundamentally a low side switch. It is placed between the load and ground. When your microcontroller sends a positive voltage to an NPN's base, it opens the channel, allowing current to drop down through the load and sink straight into ground. Conversely, a PNP transistor acts as a high-side switch. It is placed between the positive power supply and the load. To activate a PNP, you must pull its base low, grounding it relative to its emitter. This allows current to surge out from the positive supply rail, source through the transistor, and flood into the load below it. Part 3. The 5-volt logic trap. This difference introduces a dangerous trap when interfacing with microcontrollers like an Arduino or ESP32. Let's say you want to control a 12-volt motor using a high-side PNP switch. Because a PNP turns off only when the base voltage matches the emitter voltage, you need to supply 12 volts to its base to shut it off. If your microcontroller pin tops out at 5 volts, the base remains at a lower potential than the 12-volt emitter. The transistor stays permanently turned on, completely bypassing your code and potentially sending destructive reverse voltages back into your MCU pins. To solve this logic trap, engineers use a small NPN transistor to pull the base of the high-side PNP down to ground, creating a safe, isolated level-shifting driver circuit.
So, which configuration is better? For the vast majority of simple digital logic and switching tasks, NPN transistors are highly preferred. Because electrons travel faster through silicon than holes do, NPN transistors switch significantly faster, have lower internal resistance, and are cheaper to manufacture. Use an NPN when you need a simple, fast, low-side ground switch. Reach for a PNP when you absolutely must control the positive power delivery line directly. Drop a comment below if you've ever fallen into the high-side logic voltage trap. Hit like, subscribe to the channel, and keep your workbench powered up. See you next time.